have with me a rectangular frame on which I have wound a coil of wire. In the last lesson we found that if such a coil is rotated in a magnetic field, imagine that there is a magnetic field directed from the floor to the ceiling. There are lines of force going from the floor to the ceiling. If I rotate this inside that magnetic field, this coil will be cutting the lines of force. And when you keep rotating it, the rate at which the lines of force will be cut will be different for different angles. Now, the angle we will be considering here is the angle between the normal to the plane of the coil and the magnetic field. Well, we know that as the flux linked with the coil changes, that change in the flux will induce an EMF in the coil, and hence a current will flow. When the conductor is moving down, if the induced EMF is in one direction, when it moves up, the direction will change. That means for one complete rotation of this coil, the direction of the induced EMF will change completely. Now, this is how alternating current is generated. So that's the theme of our discussion today. Alternating current. A coil rotating in a magnetic field will have a current induced in it. When the coil rotates inside the magnetic field, here I have represented a magnetic field that is directed from left to right, and we have a coil that is rotated in. The flux linked with the coil changes continuously, and this induces an EMF in the coil. That's what we have been talking about so far. However, there is another way to change the flux linked with the coil. You can keep the coil stationary and rotate the magnetic field. So, the flux linked with the armature coil, the coil wound on a frame is actually called the armature coil. The flux linked with the armature can also be changed by keeping the coil stationary and moving the magnetic field. Now, for each rotation of the coil, the direction of the induced EMF and hence the direction of the current will change. Now, such a generator is called an AC generator. I have a diagram here. You can see the direction of the magnetic field and the coil, and look at the angle theta. Now, if this is the plane of the coil, this is the normal to that plane, and this is the direction of the magnetic field, and this is the angle theta. Angle theta is the angle between the normal to the plane and the magnetic field. That means at any given instant, the flux linked with that coil will be B times cos theta, and of course if the coil has n turns, the total flux linked with that coil will be n times B cos theta. Well, at any given time, the normal to the plane of the coil makes an angle theta with the direction of the field. That means phi b, the flux linked with that coil, the total flux linked with a coil like this will be n the number of turns times A times B cos theta, where A is the area of the coil. Well, this we have discussed already. As the coil rotates, the angle theta is a function of time and can be written in terms of the angular frequency as theta equal to omega t. Now, you must understand that the magnetic field does not change. When the coil rotates, the magnetic field remains a constant. So what changes is the angle theta. Angle theta is a function of time, and we write it as theta equal to omega t, where omega is the angular frequency, which you are familiar with. Now, therefore, the flux linked with the coil can now be written as phi b equal to NAB cos omega t. As the coil is rotated in the magnetic field, the flux linked with the coil changes, and the induced EMF will be a measure of the rate of change of flux linked with it. And that is Faraday's law of electromagnetic induction. Well, you know that phi b equal to NAB cos omega t, and the induced EMF is negative of d phi by dt. Of course, the negative sign comes from Lenz's law. Now, that means the derivative of this quantity with respect to t, NAB is a constant, and the derivative of cos omega t will be negative omega sine omega t. I hope you have no problem there. So the two negatives will combine. That gives you the induced EMF in the armature coil is NAB omega sine omega t. Now, I would like you to have a look at this. When the coil rotates, the variable here is that angle, which is omega t. Now, what is the maximum value of that EMF? The maximum value of the EMF occurs when that angle is 90 degrees. That is, the normal to the plane of the coil and the magnetic field are at right angles. You see, if the lines of force are now like this, that will be the time the coil will be cutting the maximum number of lines of force. The rate of change of flux will be maximum when the angle is 90 degrees. At that time, sine omega t is 1, or the maximum induced EMF will be NAB omega. So this quantity can now be called E max. Is that right? So I can say induced EMF E is E max, maximum EMF, times sine omega t. Or the induced EMF therefore is a function of time. It is a sine function. Now, when the coil moves up, if the induced EMF is from A to B, you see, if the coil moves up, what I mean is this side moves up. If the induced EMF is from A to B, on the top side, when that side moves down, now watch it here, this is the side I'm talking about. When that side moves up, if the induced EMF is from A to B, as it moves down, the induced EMF will be from B to A. That's something that you need to really understand. Now, for each rotation of the coil, the direction of the induced EMF and hence the direction of the induced current will reverse. And that's why we call it the alternating current. The number of times the direction of current reverses per second, which is the same as the number of rotations per second, is called the frequency of the AC. The normal AC that we use in our homes and offices has a frequency of 60 Hertz. That means the coil that generates the current will rotate 60 times inside the magnetic field. Alright. The frequency F and the angular frequency omega are related. Can you tell me what a relation is? We have been talking about it from Physics 1. That relation is omega equal to 2 pi F. You cannot forget that relation. Now, since E equal to NAB omega sine omega t, the maximum value of E occurs when sine omega t is 1. And we will represent this quantity NAB omega as E max because that is the maximum value of the EMF. And so we can write E max is NAB omega, where of course omega is 2 pi F. we can now write E of t, the induced EMF at any given time, is E max times sine omega t, that omega is replaced by 2 pi f. This induced voltage gives rise to an induced current. Now, if this is the induced EMF, can you write the expression for the induced current? It will be a similar expression. I, as a function of time, will be I max sine 2 pi ft. So this is the equation for the induced current, which is actually derived from the equation for the induced EMF. Well, the figure illustrates how the voltage changes with time. The voltage is a sine function. You can see this is how the voltage changes for one complete rotation of the coil, and that time is called the period. And of course that the maximum current or maximum EMF is the amplitude or the peak voltage. The peak voltage is from the negative maximum to the positive maximum, or that's the peak to peak voltage. Now, when the plane of the coil is perpendicular to B, theta equal to 0, and no change in flux occurs, and the induced voltage is 0. We talked about this already, so we don't need to do that again. How the voltage changes from 0 to a maximum, then back to 0. You can see here, now, the induced EMF at this position is actually 0. Now, the induced EMF increases, reaches a maximum when the number of lines of force cut are maximum, and then the coil begins to rotate in the opposite direction. The EMF increases in the negative direction and comes back to 0 when the rotation is complete. So once again, the induced EMF is 0, maximum, 0, negative maximum, and back to 0 for one complete rotation. Alright. Now here you have an illustration of how that happens. As this coil is rotated in the magnetic field, the EMF increases to maximum, to 0, negative maximum, 0, and it continues. Well, that is a good illustration of how the alternating generator works. Now, when we talked about direct current circuits, we had a symbol for representing a battery. In the same way, when we use an alternating current source, we will use the symbol. This is the symbol for an alternating current. We will be using this very often in this lesson. So we will also refer to this as the generator that generates the alternating current. In an alternating current circuit, we use this symbol in place of the battery that we have seen earlier. Alright, let's now talk about the alternating current in a resistor. Well, we know about direct current in a resistor, controlled by Ohm's law. Is that right? The potential difference V equal to IR. Is that valid for alternating current? Well, I have here a circuit. This is the generator connected to a resistor R. When we apply an AC voltage to a resistor, the current will flow through the resistor. But remember that current will be varying and alternating. Can we apply Ohm's law as we did with the DC? Well, how can we even specify the AC voltage since it is constantly changing? Therefore, before we talk about this, we need to talk about how we deal with such a changing voltage. An AC voltage never remains steady. So, let's first of all talk about the RMS value of an AC. The RMS value is something that is familiar to you. Root mean square. a quantity that is continuously changing and reversing in direction, if you take the average value over a period of time, it will be 0. And therefore, to deal with it, we talk about the root mean square. If you remember how we obtained the root mean square velocities of moving molecules, it's the same concept here. When you have a value varying sinusoidally, the average value will be 0 because half the time the values are positive and the other half the values are negative. One way to deal with this is to describe what we call the RMS value. What does RMS value stands for? It stands for root mean square. In other words, we take the square root of the average of the squares of all the current or EMF. That is the root mean square. To calculate the RMS value of an alternating current, we first square all the I values to make sure that they are all positive. Then we take the average of all that, and once you find the average of all the I squared values, then we take the square root. That is what we call the root mean square value. So IRMS, the root mean square value of the current, is square root of the average of all the I squared. And that will be, the instantaneous value is I0 sine omega t. So square root of I squared sine omega t squared. And this can be shown to be equal to I max divided by square root of 2. Now, what I want you to do is to recognize the relation between IRMS and I max. The RMS value of the current is related to the maximum current as IRMS equal to I max divided by square root 2. In the same way, the EMF is also related as ERMS equal to E max divided by, so VRMS, or the RMS value of the voltage, is V max, the maximum value of the voltage, divided by square root of 2. We will use these very often. That means I max equal to IRMS times square root 2, and V max is VRMS divided by square root of 2. Well, when we talk about the 110 voltage AC that we use at home, is that the RMS value or the peak value or the maximum value? Well, of course it is the RMS value and not the peak value. Now, in a resistor, the voltage and current are in phase. What does that mean? The voltage and current are in phase. It means when the voltage increases, the current also increases along with it, and when the voltage is a maximum, the current is a maximum, and so on. They are in phase. Now, you can see here, as the voltage increases, the current also increases. The voltage is 0, the current is 0, so the voltage and the current are in phase. Now, we can use Ohm's law to establish a relation between voltage and current. Yes, when an AC passes through a resistor, we can use Ohm's law, and that will give us a relation between VRMS and IRMS, as VRMS equal to IRMS times R, or IRMS equal to VRMS divided by R. How about the average power? The average power will be always positive. Is that right? Because the average power is ERMS multiplied by IRMS. Because E and I are in phase, when E is negative, I also is negative, so the product will be positive. So although I can be positive, and I can be positive or negative. E also can be positive or negative, but the product, the power, will always be positive. Now, circuits in which current is proportional to voltage are called linear circuits. In a resistor, the current is proportional to the voltage, therefore it is a linear circuit. Now, the ratio of voltage to current in a resistor we call resistance. Is that right? Resistance is the ratio of voltage to current. Now, in the case of a resistor, the resistance does not depend on the frequency. In other words, the resistance of a conductor does not depend on how fast the coil rotates to generate that AC. It is independent of the frequency. Now, but this is not true when you consider AC that passes through a capacitor or an inductor. What is an inductor? We talked about it in the last class. Well, we will be looking at that in detail in this lesson. Now, in an alternating current circuits that contain capacitors and inductors, the ratio of voltage to current does depend on the frequency. I want you to understand this very well. For a resistor, the resistance does not depend on the ratio of voltage to current. But when an alternating current passes through a capacitor or an inductor, the ratio of voltage to current depends on the frequency of the AC. That's a big difference there. In general, in an AC circuit, there is a phase difference between voltage and current. Now, in the case of a resistor, voltage and current are in phase. And so, the ratio of voltage to current is the resistance. But in the case of a capacitor or an inductor, the voltage and current are not in phase. So we can say, in general, in an AC circuit, there is a phase difference between voltage and current. The only exception is the resistance, where they are in phase. Now, in such a case, the ratio of voltage to current is called the impedance of the circuit, and we represent that by Z. So, in the case where there is a phase difference between voltage and current, you will not call the quantity, the ratio of voltage to current, resistance, but we call it impedance. In fact, resistance is a special case of impedance. In the case where the voltage and current are out of phase by 90 degrees, this is a particular case again. Now, there are two particular cases we are discussing. Where the phase difference is 0, that impedance is called the resistance. And that is the case of the resistor. If the phase difference is 90 degrees, that means the voltage and current are out of phase by 90 degrees, then that impedance is called the reactance. The reactance, and will be represented by uppercase X. The reactance of a capacitor will be written as X sub C, and the reactance of an inductor will be written X sub L. If you remember, we used L for inductance of a coil. And it is measured in the same unit as resistance, namely ohms. Alright, let's do an example. A 12 ohm resistor is connected across an alternating EMF that has a peak value of 48 volts. So this is the maximum voltage. Find the RMS current, the average power, and the maximum power. It's a very simple direct application. You know that Vmax is given to be 48 volts. And we need to find the VRMS, we need to find the RMS current. If you want to find the RMS current, we need the RMS voltage. Vrms is Vmax divided by square root of 2. And that will be 48 volts divided by square root 2, that is 33.9 volts. Once you know the value of Vrms, then Irms is Vrms divided by the resistance which is given, and so that will be 2.83 ampere. We need to find the average power. The average power is the product of Vrms and Irms, and we know both these values, and that gives you the average power as 96 watt. What is the maximum power? The maximum power will be the product of Vmax and Imax. And in order to find Imax, well, Imax is square root 2 times Irms, and that will be 4 ampere. Therefore, maximum power is Vmax times Imax, that is 192 watts. Alright, let's now talk about capacitors in AC circuits. Now, remember, a current flows through a capacitor only when the voltage across changes. When the voltage remains steady across the capacitor, the current does not flow. Well, that is very important in this case. Whereas resistors allow a flow of electrons through them directly proportional to the voltage drop, capacitors oppose change in voltage by drawing or supplying current as they change, as they charge or discharge. You see, a current flows through a capacitor only when they get charged or discharged. As they get charged, the potential difference across the capacitor changes, and the current flows only when the potential difference changes. When the capacitor is fully charged, it has a constant potential. There will be no current flowing in the capacitor. Now here I have a diagram of an AC generator connected to a capacitor of capacitance C. Now, the flow of electrons through a capacitor is directly proportional to the rate of change of voltage. You see, when the voltage is steady, there is no flow of charges into a capacitor. So, the flow of electrons through a capacitor is directly proportional to the rate of change of voltage across the capacitor. Now, the current through the capacitor is a reaction against the change in voltage. Only a change in voltage will produce a current in the capacitor. I want you to watch these two drawings. Now, the blue drawings is the voltage across the capacitor, and the red, I don't think it shows as red in the broken lines. Now, look at the slope of the blue line. The slope is maximum here, the slope reduces and becomes 0. So the rate of change of voltage is maximum. That means that is when the current is maximum. And when the voltage is peaked, the rate of change of voltage is 0. That is when the current is 0. Alright. So the instantaneous current is 0 whenever the instantaneous voltage is at a peak, and instantaneous current is at a peak whenever the voltage is changing at the maximum rate. So you must now understand this. Now see how a phase difference comes about between voltage and current. Now this results in a voltage wave that is minus 90 degrees out of phase with the current. You can see when the current is a maximum, the voltage is 0. So we say that current is ahead of the voltage by 90 degrees. There you are. The current is ahead of the voltage by 90 degrees. That's the representation. We say the voltage lags behind. Voltage lags behind the current by 90 degrees. Now, since the voltage and current are 90 degrees out of phase, the capacitor offers a reactance represented by Xc. Now, a capacitor's opposition to change in voltage translates to an opposition to an alternating voltage in general. Well, I'm not going to go into the details. Now, the reactance of the capacitor is expressed in ohms as we normally do, and is symbolized X sub C. And I want you to remember this. The value of the capacitive reactance is 1 over 2 pi Fc, where F is the frequency of the AC. Now look at this. The reactance of a capacitor is inversely proportional to the frequency of the AC. All the other quantities are constant there. So take note of that equation. The reactance of a capacitor, X sub C, is 1 over 2 pi Fc. Let's do another example. Calculate the reactance and the current in the circuit shown. Here we have an alternating current source which produces a 10 volt EMF at a frequency of 60 Hz connected to a 100 microfarad capacitor. So we got the capacitance, we got the frequency, therefore the capacitive reactance X sub C is 1 over 2 pi Fc. We know all those values. That gives you the reactance 26.53 ohms. In that case, what is the current? The current in the capacitance is Vc divided by Xc, voltage across the capacitance divided by reactance of the capacitance. And that will be 0.38 ampere. You can see all these are very simple, straightforward, one-step problems. Now, however, we need to keep in mind that the voltage and current are not in phase. The voltage lags behind the current, or we can say the current leads the voltage by 90 degrees. You can see here, if this is the current, that is the voltage. The current leads by 90 degrees. And this is the reactance of the capacitor. Another example. A 20 microfarad capacitor is placed across a generator that has a maximum EMF of 100 volt. That is the Emax. Find the capacitive reactance and the maximum current when the frequency is 60 Hz. We'll always start by picking the data and then, of course, looking at the relevant equation. The capacitive reactance X of C is 1 over 2 pi Fc, where we know the frequency is 60 Hz and the capacitance is 20 microfarad. Use them in proper units and that gives you the reactance is 132.6 ohms. Now, the maximum current is maximum voltage divided by the reactance. You can see the same situation, Ohm's law, I equal to V over R. In this case it is not R but reactance. And we know all these values. So the maximum current is 0.75 ampere. Alright, we will now see what happens when an AC is passed through an inductor. Remember, an inductor is simply a coil of wire. Now, this coil of wire is actually an inductor. Now, why is it called the inductor again? When a current grows in it, when a current goes from 0 to maximum, the coil itself is subjected to a changing magnetic flux. And that changing magnetic flux will induce an EMF in the coil which will oppose the original cause of it. Is that right? And that's why this is called an inductor. And the inductance L is measured in henries. So inductors oppose changes in current through them. Is that right? If current is increasing, the induced EMF will oppose that. If the current is decreasing, the self-induced EMF will oppose that. So inductors oppose changes in current through them by dropping a voltage directly proportional to the rate of change of current. Now, in accordance with Lenz's law, this induced voltage is always such a polarity as to maintain a current at its present value. The tendency of the inductor is to maintain the current at the present value. Why? Because if the current increases, the self-induced EMF will tend to decrease it. If the current decreases, the induced EMF will oppose that decrease. Therefore, the tendency is always to maintain the current at the present value. Now that is, if the current is increasing in magnitude, the induced voltage will push against the electron flow. If the current is decreasing, the polarity will reverse and push with the electrons to oppose the decrease. So an increasing current will be opposed by the induced current. A decreasing current also will be opposed by the induced current. This opposition to current, this opposition to change in current is called inductive reactance. You see, this opposition is similar to resistance offered by a resistor, but it's not really a resistance. We call it the inductive reactance, represented by XL. Now, the relationship between voltage dropped across the inductor and rate of current change through it is V equal to L di by dt. We saw that equation in the last class. Now, the figure shows an inductor of inductance L connected across an AC generator. The voltage drop across an inductor is a reaction against the change in current through it. Now remember, an AC is a continuously changing current or a continuously changing EMF. That means the inductor will be continuously opposing it. Now, therefore, the instantaneous voltage is zero whenever the instantaneous current is at a peak. When the instantaneous current is at a peak, the current is not changing. Only a changing current will produce an induced EMF. So look at this. The blue represents the EMF and the brown or the red represents the current. So the instantaneous voltage is zero. This is the instantaneous voltage zero when the instantaneous current is at a peak. Now here, the rate of change of current is zero. Momentarily, the current is stationary there. It's not changing. Now, when is the voltage maximum? The induced voltage is maximum when the current is changing at the maximum rate. When the rate of change of current is maximum, the induced voltage is maximum. And when the induced current is maximum, the induced voltage is zero. Thus, the current lags behind the voltage by 90 degrees. Now, if you notice, in the case of the capacitor, the current was leading the voltage by 90 degrees. In the case of the inductor, the current lags behind the voltage by 90 degrees. Voltage leads current by 90 degrees. So, in the diagram, if this is the current, that will be the EMF. The EMF or the voltage leads the current by 90 degrees. Now, because instantaneous power is the product of the instantaneous voltage and the instantaneous current, the power is zero whenever the instantaneous current or the voltage is zero. Now tell me, in the case of the resistor, we said the average power or the instantaneous power is always positive, because when the current is negative, the voltage also is negative. The two multiplied will make it positive. But in the case of an inductor, the voltage and current are not in phase, and therefore the power can be positive or negative. Whenever the instantaneous current and voltage are both positive or both negative, the power is positive. Now there you have the graph for the power. The green curve represents the power. The blue represents the voltage. The brown represents the current, and the green represents the power. And you can see the power is zero when the current is zero, when the voltage is zero. So wherever the current or voltage is zero, the power is zero. And the power is positive when both voltage and current are positive, or when both are negative. And when one is positive and the other negative, the power is negative. However, because the current and voltage waves are 90 degrees out of phase, there are times when one is positive while the other is negative, resulting in equally frequent occurrence of negative instantaneous power. Positive instantaneous power and negative instantaneous power. Now, what does negative power mean? See, normally when you talk about the power that is in a circuit, in a resistor, for example, it is actually consuming power. It is actually absorbing power from the circuit. But in an inductor, the inductor not only absorbs power, it also releases power to the circuit. So negative power means that the inductor is releasing power back to the circuit, while positive power means that it is absorbing power from the circuit. So, since the positive and negative power cycles are equal in magnitude and duration over the time, the inductor releases just as much power back to the circuit as it absorbs over a span of a complete cycle. That means the net power used by an inductor is zero. So this means that the reactance of an inductor dissipates a net energy of zero, unlike the resistance of a resistor, which dissipates energy in the form of heat. It doesn't happen in the case of an inductor. The reactance XL in ohms for any inductor is directly proportional to the frequency. You must distinguish again here. For a capacitor, the reactance is inversely proportional to the frequency. For an inductor, the inductive reactance XL is directly proportional to the frequency. And look at the equation. XL is 2 pi FL, and since 2 pi F is angular frequency omega, we can also write it as omega L. So, going back to the capacitor, X sub C is 1 over 2 pi FC, whereas for an inductor, X sub L is 2 pi FL. Take note of these. Example 4. An inductor of inductance 10 millihenry is connected across a 10-volt generator. Calculate the reactance in the circuit and the maximum voltage and the maximum current. Well, what are the things we know? We got the ERMS is 10 volt, the frequency is 60 hertz, and the inductance is 10 millihenry. we want to calculate the reactance. The reactance X sub L is 2 pi FL. We have all these quantities, and that is 3.770. The maximum voltage, E max, is E RMS times square root of 2. See, whenever you are told that you have a 10 volt generator, that 10 volt is the RMS value, not the peak value. So E max is E RMS times square root 2, and E RMS is given, so the peak value of the EMF is 14.1 volts. And therefore, what is I max? I max is E max divided by XL. Like Ohm's law, I equal to V over R. Here, I max is E max over XL, and we know both those values. So the maximum current is 3.74 ampere. Another example. A 40 millihenry inductor is placed across an AC generator that has a maximum EMF of, this time you are given E max. Find the inductive reactance and the maximum current when the frequency is 2000 Hertz. So always read the question carefully and see what is given. You got, first we calculate the inductive reactance. XL is 2 pi FL. We have all those quantities, and that will be 502.70. I max is E max divided by XL. E max we know, XL we just calculated, and that will be 0.24 ampere is the maximum current. Well, that was a very simple problem. Let's now look at LCR circuit. What does LCR stands for? We have an inductor, capacitor, and a resistor all combined in one circuit, an LCR circuit. You know by now that in a pure resistor circuit, voltage and current are in phase. In a capacitor circuit, current leads the voltage by 90 degrees. In an inductor circuit, the voltage leads the current by 90 degrees. Well, what happens when all these three are connected? Here we have an alternating current source connected to a resistor R, an inductor L, and a capacitor C. I have used some values. We can ignore them at this time. So a resistor of resistance R, a capacitor of capacitance C, an inductor of inductance L are in series and connected across a generator of EMF E. Well, of course, that is the RMS value. The current in the circuit is determined by the inductive reactance XL, the capacitive reactance XC, and the resistance R. So it's a combination of all these three that is going to determine the total current. Now, if F is the frequency of the AC, then you know that the inductive reactance is 2 pi FL, and the capacitive reactance is 1 over 2 pi FC, and the resistance is R. Now, if VL is the voltage across the inductor, and VC the voltage across the capacitor, VR the resistance across the voltage across the resistor, not the resistance across the resistor, the voltage across the resistor, then you know that VL equal to I times XL. That is the equation for the inductor. Is that right? The basic Ohm's law, V equal to IR. Replace R by the reactance. So VL is IXL, VC equal to IXC, and of course VR equal to IR. Those are the individual equations that gives you the voltages across each of these. The potential drop across the resistor and that across the reactance are at right angles to each other. Is that right? Yes. The potential drop across each of these are not in phase. the current in an AC circuit not only depends on the resistance value but also on the reactance. Since the reactances XL and XC are 100 degrees out of phase, you see, if XL is upward, then XC will be downward. Because in a capacitor, the current leads by 90 degrees. In an inductor, the voltage leads by 90 degrees. So there is a phase difference between XL and XC of 180 degrees. Therefore, the net reactance, when you have the two of them together, because if one is upward, the other is downward, the net reactance will be XL minus XC. Well, either XL minus XC or XC minus XL, it doesn't matter. So here, if this is XL, this is XC, and this is the resistance. So these are the three components in that circuit. The resistance is at right angles to both XL and XC. Now, the combined effect of resistance and inductance in a circuit is called the impedance. We talked about this, represented by Z. The total effect of all these reactance and resistance together we call impedance. And if this is the total impedance, it is due to the net reactance. Look at this, XL minus XC is this vector. R is this vector. Therefore, the total impedance is the third side, which is the Z. So Z squared equal to R squared plus XL minus XC squared. So this is the total impedance for the LCR circuit. And what is the current in the circuit? The current is determined by the impedance. So that will be I equal to V over Z. Power P is ERMS times IRMS cos phi, where phi is the angle between the resistance and the impedance. And the tangent of that angle is XL minus XC divided by R. And cos phi equal to R divided by Z is called the power factor of the LCR circuit. Now that's one term that you need to remember. Cos phi, which is R divided by Z, is called the power factor of the LCR circuit. Now, what is a resonant circuit? Very often this is used in electrical engineering. In a circuit, if the inductance and the capacitance values are such that XL equal to XZ. Now remember, XL and XC are 180 degrees out of phase. That means if the magnitudes of these are the same, then XL minus XC will be equal to 0. Now, such a circuit will be now controlled only by the resistance. So the total impedance then will be equal to the resistance only. The current then will be a maximum because the reactance, the net reactance is 0. The maximum current then will be I equal to V over R. And such a circuit is said to be a resonant circuit. When the circuit is adjusted for resonance, the net reactance is 0. The maximum current, the current will be a maximum at that time. And we have a resonant circuit. In fact, when you tune a radio or television, you're actually tuning using the condition of a resonant circuit. So the condition for resonance is XL equal to XZ. XL is 2 pi FL. XC is 1 over 2 pi FC. So if F0 is the resonant frequency, then 2 pi F0L will be equal to 1 over 2 pi F0C. Now, when this happens, we call the frequency to be the resonant frequency, and we represent it by F0. Can you use this to solve for the resonant frequency? It's very simple. Cross multiply and solve for F0. F0 will be 1 over 2 pi square root L times C. You will see this a lot in electrical engineering. Let's do an example. Find the impedance and the current in the circuit shown on the right. All the values we have E equal to 110 volts, that's the RMS value. The frequency of the AC is 50 Hertz. The resistor has a value 4 ohms. The inductance is 27 millihenry, and the capacitance of the capacitor is 380 microfarad. Well, we got the frequency, inductance, capacitance. First we find XL and XC. Simply use the formula. XL is 2 pi FL, and that will be 8.48 ohm. And how about XC? XC is 1 over 2 pi FC. Use all the given values. That will give you 8.38 ohm. Well, if you see here, it's almost a resonant circuit because the two reactances are almost equal. In other words, because they are 180 degrees out of phase, the net reactance is XL minus XC is 0.1 ohm. It's a very small quantity. So what's the impedance? The impedance is square root of R squared plus XL minus XC squared. So that will be, I'm going to use that XL minus XC, the net reactance. So Z equal to square root of R squared plus X squared, and that's equal to 4.001 ohm. You got the total impedance, and that can be used now to find the total current. I equal to V RMS divided by Z. V RMS is given to us 110 volts. Therefore, I RMS is 27.5 ampere. Now, F0 is 1 over 2 pi square root LC. F0 is the resonant frequency, and that will be, using the values of L and C, it will be 49.7 Hertz. The one we have used is 50 Hertz. So if the frequency now change slightly, that will be the resonant frequency of that circuit. At that frequency, the capacitive reactance will be equal to the inductive reactance. They will cancel each other, and the circuit will be purely a resistive circuit. Alright, another example. A series LCR circuit with L equal to 2 Henry, C equal to 2 microfarad, and R equal to 20 ohm is driven by a generator with a maximum EMF of 100 volts and a variable frequency. Find the resonant frequency F0, the power factor for the circuit when F equal to 64 Hertz. Well, first, resonant frequency. F0 is 1 over 2 pi square root LC. We know all those values. The resonant frequency is 80 Hertz. The inductive reactance is 2 pi FL, and using the values we have 804 ohm. And the capacitive reactance, by using the given values, is 1239 ohm. So what is the net reactance? Net reactance is XL minus XC, that is negative 430 ohm. What's the total impedance? Total impedance is square root R squared plus X squared, where X is the net reactance, and that will be, we have now calculated X. You can see that negative value will disappear when it is squared. So the net impedance is 430.5 ohm. We need to find the power factor. The power factor is cos phi. If you remember that diagram we had, cos phi is R divided by Z. So we got R and we got Z. Therefore, cos phi equal to R over Z. That will be 0.046. Another example. In the figure shown, find the RMS voltage across points BC, AD and BD. Oh, you are. That's AD. Alright, we need to find the RMS voltage across BC, across AD and across BD. Well, the voltage across BD is the voltage across the combination of resistor and inductor. Across AD is the voltage across the capacitor. Is that right? So voltage V across 2 points is current multiplied by the resistance, reactance, impedance, whatever is the case. So in order to find the voltage across BC, it is the current multiplied by the resistance. If you want to find the voltage across BD, it is the reactance of the system multiplied by the current. Alright, so we got R equal to 75 ohm, frequency is 60 Hertz, the ERMS is 120 volts, L equal to 0.2 Henry, and the capacitance is 100 microfarad, which is 10 to the power of negative 4 of a farad. Now, first of all, XL is 2 pi FL, and using the values we get 75.4 ohm. And XC is 1 over 2 pi FC. Again, using these values we have 26.53 ohms. Now remember, in the lecture I am really going fast with it, but you got to stay back and do these calculations on your own. Alright. So we have that's R, and that's your XL, and that's your XC. I hope you remember that diagram. Now, the yellow line, I think it has gone out of the screen. XL minus XC, you can now calculate XL minus XC, and the impedance Z will be square root of R squared plus XL minus XC squared. There you are. Now, we got all these values, and substituting them, we got the total impedance is 89.5 ohms. Okay, we've got the RMS value of the voltage, and we have the total impedance of the circuit. Therefore, we can calculate the RMS value of the current. What is IRMS equal to? IRMS is ERMS divided by the total impedance. So ERMS divided by Z, that will be 1.34 ampere. We now know the total current in the circuit. We can now calculate the potential difference across any 2 points. That's what we want. We want to find the potential difference across BC. Now, potential difference across BC is the potential difference across the resistor. That will be IRMS times R. The potential difference across CD will be the potential difference across the inductor, that is IRMS times XL, the inductance. Now across AD will be the potential drop across the capacitor, which will be the current in it, which is IRMS we calculated, times XC, and so on. Let's do that. So we have all these. The voltage across BC is the voltage drop across the resistor. VBC is IRMS times R, which is 100.5 volts. The voltage across CD is the potential drop across the inductor, which is VCD is IRMS times the inductive reactance. We have those values. Similarly, the voltage across AD is the potential drop across the capacitor. VAD is IRMS times the reactance of the capacitor. We have all those values. And finally, the potential drop across BD. The potential drop across BD is the potential drop across a series combination of the resistor and the inductor. Of course, there you got to calculate the total impedance. Since the potential drop across the inductor is 90 degrees out of phase with across the resistor, they are at right angles to each other, and the resultant voltage therefore is, well, VR is 100.5 volts. That is the potential drop across the resistor we calculated. And the potential drop across the inductor, we know VCD is 101 volts. And these two are at right angles. Therefore, the potential drop across BD will be the resultant there. And VBD will be VBC squared plus VCD squared, and that will be 141.8 volts. I think you probably need to look at this one more time. Alright, we will now see another application of electromagnetic induction. In the last lesson I told you, if the current in a coil of wire is either growing or decaying, the associated change in magnetic flux can actually induce an EMF in another coil of wire. Now, what happens if I allow an AC to pass through this coil? Remember, an AC is continuously changing. It is growing, decaying at a tremendous rate, about 60 times a second. Now, if I have another coil inside the first coil, and we use an iron core to magnify the magnetic field, then the magnetic flux linked with this will be continuously changing, and we would expect an EMF and hence a current to be induced in here. If you notice, I have connected this coil, which I'm going to call the secondary coil, to a light bulb. And the light bulb will tell you if there is a current in it or not. This is the primary coil. I'm going to connect it to an AC and see what happens. I'm going to put this secondary coil in there and see if anything happens when I connect it. Look at this. The light bulb is lighting up. That means the continuously changing magnetic field produced by the AC is actually inducing an EMF. You see, this is not connected to the power supply. And you can see if I withdraw it, the magnetic flux linked with that coil decreases and the induced EMF also decreases. Now, this is the principle of a transformer. So we will quickly talk about that before we close the lesson today. So the transformer consists of an iron core on which one coil of wire is connected to an AC source, and another coil of wire can be connected to a bulb or a galvanometer. When the AC is turned on in the first coil and AC is generated in the second coil, the changing magnetic flux produced by the AC in the first coil will induce an EMF in the second coil. Now, the changing magnetic flux produced by the AC is responsible for that induced EMF. Now, an alternating current flowing in the top coil will result in the production of an alternating current in the bottom coil. Now, the top coil is called the primary coil, and the bottom one is called the secondary coil. So a transformer has a primary coil and a secondary coil. Now suppose N1 is the number of turns in the primary and E1 is the input voltage. Is that right? That's the input voltage. And if N2 is the number of turns in the secondary and E2 is the output voltage. So for a transformer there is an input voltage and an output voltage. Now there's a relation connecting E1, E2, N1 and N2. And I'll give you that relation in a while. The transformer is represented by this symbol in an electrical circuit. Now, a relation between E1, E2, N1 and N2 is E1 divided by E2 equal to N1 divided by N2. Very simple relation. Now, that means you can either have a step-down transformer or a step-up transformer. Now, if N2 is less than N1, the number of turns in the secondary is less than the number of turns in the primary, then the output voltage will be less than the input voltage. That means from a high voltage AC, you can obtain a low voltage AC. So this is a high voltage AC and the output is a low voltage AC. This kind of a transformer is called a step-down transformer. Now, what is therefore a step-up transformer? If N2, the primary number of windings, the secondary number of windings is greater than the primary number of windings, then the secondary voltage or the output voltage will be greater than the input voltage. So here we have a primary coil which the number of turns, the secondary coil has a greater number of turns. In this case, you get a bigger output across the secondary, and such a transformer is a step-up transformer. You can actually use a low voltage AC and obtain a high voltage AC. Now, but we can get an output voltage that is greater than the input voltage. Does it mean that the transformer is creating energy? Well, the total energy cannot change. So the input power and the output power, in fact the output power can never be greater than the input power. If E1 and E2 are the primary and secondary voltages and I1 and I2 are the primary and secondary currents, then we have the maximum we can have is E1 I1 equal to E2 I2, the input power equal to the output power. But in practice, some power is lost in the transformer in the form of heat and sound. So this will not be in practice. This is ideal. Now this means that for a step-down transformer, when E2 becomes less than E1, I2 will be greater. For a step-down transformer, the output current will be greater than the input current when the output voltage is less than the input voltage. Similarly, for a step-up transformer, when you step up the voltage, you step down the current. You can't have both step up at the same time. Now, transformers are very useful in transmitting power over distances. Now, in the power plant, electricity is generated at say about 15,000 or 20,000 volts. And now it is stepped up into say 400,000 volts, and here is the high tension voltage. It then comes to the distribution where you have a step down transformer which steps it down to about 4,000 volts, which is the line that comes to your house. And outside your house always there is a transformer, a step down transformer, which steps down that 4,000 volts to 120 volts so that you can use them. So all these are very important applications of electromagnetic induction. Alright, so on the phone pole next to your home, the 13 kV, actually the line that comes to your home is a 13 kilovolt, it is stepped down to 120 or 240. In fact, there are both these that are the outputs for your transformer. Let's do a problem. A doorbell works on a 6-volt supply and it takes in 0.5 ampere when operating. A step-down transformer with 2,500 turns in the primary is used to step down the 120 volts to 6 volts. It's very commonly used in homes. What is the number of turns required for the secondary coil? What is the current in the secondary coil? Well, we have E1, the primary voltage, E2, the secondary voltage, N1, the primary windings, and I1, the primary current. We have E1 over E2 equal to N1 over N2, and that gives you N2 equal to E2 N1 over E1, and that will be 125 turns. And then E1 I1 equal to E2 I2, and that will give you I2, the output current or the secondary current is E1 I1 over E2, which is 10 ampere. Well, that's a very simple problem, and you can actually see problems like this, applications of this in